Hey there guys, welcome back to a brand new math video. So today we are going to show for a 2x2 matrix A, then det A transpose is indeed equal to det A squared. And we are going to make a general consensus here, and in another video we will find a solution for the n by n matrix. And see if that can stand. In fact it can, but we will prove it. So let's go ahead and let's define a matrix A. Let's let A equal the matrix A, B, C, D only when A, B, C, and D are elements of the real number line. Okay? That is important in this particular proof. If you're looking at Zn, then it would be a bit different. And now let's go ahead and let's prove this statement first, det A squared. Let's find that. So let's go ahead and find det A. The determinant of A by matrix properties is nothing but A, D, take away BC. But we are interested in det A squared. So det A squared is just this squared. AD minus BC squared. Okay? And that is part one for this proof. And now let's go ahead and find this. So we need A transpose. A transpose is going to be nothing but this becomes the row and this becomes the row, and the columns sort of shift as well. So we get AC, BD. So we get that as A transpose. Now let's move over here and do some working over on this side of the whiteboard, and let's find A transpose. So A transpose is nothing but A, B, C, D, that's supposed to be a D, multiplied by the matrix AC, BD. Now we can use some multiplication rules of matrices to find this. So we take this row and multiply it by this column to get the first element. So we get A squared plus B squared is that. And now we go ahead, take the same row and multiply it by this column to get the righter hand side of the top matrix input. So we get AC plus BD. And now we do the same here. We take that and multiply it by that to get the bottom of the left input for this matrix element. So we get the same thing as this. We get AC plus BD, because C times A plus B times D is exactly that. And then our last element is C squared plus D squared. C squared plus D squared. Okay? And that is A transpose. Now, we can take the determinant of this matrix. We can take the determinant just by going det of A transpose is nothing but A squared plus B squared multiplied by C squared plus D squared, take away, and we've got AC plus BD squared. Okay? And what we see there is that this is all squares. We see that that is always positive, that's always positive, and this is always positive. And when this is positive, then that's negative. So, yeah. Now we have to try and prove that this is nothing but this. So how should we go about doing that? Should we expand? We could try and expand this, or we could try and expand this. Or we could do both and prove that LHS, the left-hand side, is equal to the right-hand side. But what we are going to do is we are going to expand this result and see if we can actually simplify it down. I already can see that there will be some simplifications here. And let's do that. Let's flip over the whiteboard, get a clean side there. Hopefully this doesn't bugger up the manual focus. No, it did not. Let's erase what I had there. Is that a mark in it? I hope not. Oh no, it's just a bit of red ink. So we found that det, the determinant of AA transpose, was nothing but A squared plus B squared multiplied by C squared plus D squared. Take away. Let me have a look on the other side. Memory's bad. Take away AC plus BD squared. AC minus BD squared. Okay? Just double check that. That's supposed to be a plus? Okay. That is my bad. Okay, so we've this, and now we can expand it. Expanding, we get A squared, C squared, plus A squared, D squared, plus B squared, C squared, plus B squared, D squared. Take away, and this expands to A squared, C squared, plus 2AC BD. We will rearrange that to be in alphabetical order because that really does trigger me. You guys can see that alright? Yes, you can. And now we get plus D squared B squared. And that simplifies further because we get that cancelling with that and that. And we get D squared B squared cancelling with that and that. And we get the statement A squared D squared plus B squared C squared take away to A, B, C, D, and that is nothing but the left hand side expanded. So if we take a look back over here, we add that. So if we were to simplify and factor this out, we'd get nothing but AD take away BC squared. Okay? So that is congruent. My pronunciation is really bad. That is nothing but det of A squared. And you might be wondering, okay, how is that possible? What can we use? What can we use this, and how can we use this in real life, basically? Well, there is actually a property that you can use. So the determinant of, let's say, AB is nothing but equal to the determinant of A multiplied by the determinant of B. And now if we let that B equal nothing but A transpose, then we get det of A multiplied by det of A transpose. And if we were to find the determinant of A transpose, in fact, let's do that. Let's show that. Let's do that. So the det of A transpose, where A transpose was nothing but the transpose of A, we would find that that is actually equal to det of A, and we will prove that. I'm just trying to think. AC, AC, yeah. So A transpose was equal to our matrix A, C, B, D. Yep, that's right. And we can take the determinant of that and we get det. The determinant of A transpose is nothing but AD minus BC. And if we were to look back at what we found over here, we see that, well, we get AD minus BC here as well. And hence, we found that det A is nothing the same as det A transpose in a 2 by 2 matrix. But is this true for an n by n matrix? That's what I want to figure out in the next video. But this is how that works. That's how we found that det A transpose is indeed det A squared. Okay? So that is it for this video. I hope you guys are enjoying these math videos as much as I am filming them. I think my explanations can get a bit confusing at times of what I am doing, but I will try to work on that in the future videos. But, you know, I've only started out with these types of videos. They will get better. So guys, I hope you guys subscribe for more content. Twitter and Instagram links are in the description. And I'll see you guys in the next video.